Hello, in this video we're going to lay the foundation for working with matrices in order to solve systems of equations. So we're going to begin with this idea of an augmented matrix. We can represent any system of equations in what we call an augmented matrix. So that's when we take a system of equations that looks like this, which should be familiar to you, and then we rewrite it as a matrix without any of the variables. So notice what's happened here is that on the left side of the matrix, the left side of this vertical line, we have the coefficients of the x and the y terms. So 4 is the coefficient of x, so a 4 goes here. And 3 is a coefficient of y, and so the 3 goes here right next to it. For the second equation, the coefficient of x here is a 1, so we put a 1 in the coefficient matrix, and the coefficient of negative 3y is negative 3. Notice that we have 3 columns that we've created in this augmented matrix. The first column represents all of the coefficients for the x terms in our equations. The second column represents all of the coefficients of the y terms in our system. And the third column represents all of the constant terms that are on the right side of these two equations in the original system. So this is what we call a coefficient matrix. And as you will see, this is very handy when solving this system of equation when we have a more complicated equation. For example, let's say I have a system of equations with 3 equations and 3 unknowns. I have variables x, y, and z. Solving this system by manipulating the equations with substitution or other addition methods can be pretty cumbersome. So what we're trying to move towards is a way to solve this system in an efficient way without having to do too much algebra. So we're going to write this system of equations in different formats. For example, if I write this as an augmented matrix, you can see here that x plus 3y minus 3z equals 200 becomes 1 for the 1x, 3 for the 3y, and negative 3 for the negative 3z. And then the vertical line, and over here on the constant terms, we have 200. Likewise, you can see the second equation has a coefficient of negative 2, negative 5, 9, and 0. And you see those numbers down here in the second row of the augmented matrix. And then finally, the last row, or the last equation, has a leading coefficient for the x term of negative 1, so that goes here. Negative 2 for the y term goes here, and positive 7 goes down here. And then, of course, the constant term is 300. So we have at least succeeded in rewriting the system of equations without all of the variables. Now I'm going to do something that I'm not going to explain quite yet, but I'm just going to make the claim that this matrix is equivalent. In other words, it gives the same solution as this one. So what you'll notice here is that the first line or the first row in this matrix is exactly the same as the one before it. But the second row and the third row are completely different. But notice something. This last row tells me that 0x plus 0y plus 1z is equal to 100. In other words, 1z, or z, is equal to 100. And therefore, I actually know part of my solution. I know that z is 100. Now think about this for a moment. If I know that z is 100, then I can substitute that value up into this equation right above it that says that 1y plus 3z is equal to 400. But if I know that z is 100, then 3 times z would be 3 times 100. So you can start to get the idea that if I can get the matrix in a more simplified form with a few zeros hanging out, and some ones, it's going to be relatively easy to determine the solution for this system. And that's only going to be true if this matrix is equivalent to this matrix. And again, what I mean by that is that the solutions that you get from one matrix is the same as the solutions you get from the second matrix. So let's take a look at some key attributes of this matrix. Notice, where are the ones? Also notice, where are the zeros? So let's explore that a little bit. First, notice that what we call this is the row echelon form. So here's another example of a row echelon form matrix. First of all, any rows that are all 0 will be at the bottom. So I have a row of zeros down here, and that goes at the bottom. It will not be in row echelon form if this row of zeros was anywhere else up here. The second thing to notice in a row echelon form is that the first number in any non-zero row should be a 1. So the very first number in the first row you can see here is a 1. The very first number in the second row, not counting 0, is a 1 right here. And the first number in the third row, except for the zeros, is a 1 right here. So the ones basically always end up being along a diagonal. Next, any leading 1 in a row is below and to the right of the previous leading 1 from the row above it. So this 1 right here in row number 2 is below and to the right of the 1 above it. This 1 in row 3 is below and to the right of the 1 above it. So again, this is basically just another way of saying that the ones are going to be along your diagonal. Finally, any column with a leading 1 will have zeros below that 1. So here's a column number 1, with a leading 1. And if it's in row echelon form, everything below it needs to be zeros. Here's a row with a leading 1, and notice that everything below it is a 0. And over here in row 3, here's a 1. Here's a row with a 1 as its leading number, and everything below it is a 0. Another way to think about this is that once you have a 1 on the diagonals, you will get all zeros below it. If you don't have all zeros below all of your 1s in the diagonal, it's not yet in row echelon form. So something to think about as we make our way through this section is that our goal is to change the leading number in each row to be a 1, and then to zero out everything below it. And that's actually how we're going to work. We're going to start right up here in the upper left corner. We're going to make sure that this is a 1, and then we're going to make sure everything below it is a 0. And once we're done with column 1, we're going to move to column 2. Now, column 2 starts up here in this example with a 2. Notice that there's nothing in these rules for row echelon form that tells me anything above the 1s. So we don't have to worry about anything above the 1s unless we really want to, but it's not required. We just have to make sure that the 1 in the diagonal position is indeed a 1, and then everything below it must be a 0. Same thing for column 3. The 1 right here is down in this lower right-hand corner, so we don't care about anything above it, like this 8 and this 1 up here. What we care about is that this is a 1, and then this below it is a 0. And that's what we call row echelon form. So keep that in mind as we make our way through the next few examples. Let's take a look at an example where we have a matrix in row echelon form that we just talked about, we could ask this question: what is the solution of this system of equations? And as I hinted at before, we can use back substitution to find it. So for example, notice that this last row doesn't really tell me anything. It says 0x plus 0y plus 0z is equal to 0. Okay, that doesn't really tell me much. But this third row tells me that 1z is equal to 4. If I know that z is equal to 4, then I can put it right up here into this second row. This tells me that 1y plus 1z is equal to 6. But if z is equal to 4, then that tells me that y plus 1y plus 4, 1z is going to give me 4, so y plus 4 is equal to 6. And then that tells me that y is equal to 2. So if I know that z is equal to 4, and I know y is equal to 2, I can put both of those values into the first equation. So I'm going to let you try that on your own, and you should get a solution that says that x is equal to negative 33, y is equal to 2, and z is equal to 4. Give that a shot, and then you can go to the next video.